Welcome to this lab how to build RAG pipelines in AI applications. Retrieval Augmented Generation, RAG, is an AI technique we use to generate accurate responses to user queries by retrieving relevant documents for the query from an external database and using them as context for a large language model, LLM, to generate outputs. This article will help you understand the basics of RAG pipelines, their components, and how they work by building a RAG pipeline using an external dataset, a vector database, and an LLM. What is a RAG pipeline? A RAG pipeline is the structured workflow that combines external data retrieval with an LLM Gamma's text generation capabilities to generate context-aware responses for a given query. A RAG pipeline consists of three stages, i.e., data ingestion, retrieval, and generation. A typical RAG pipeline looks as follows. A RAG pipeline has multiple components that perform specific tasks. Let's discuss the different components of a RAG pipeline. Components of a RAG pipeline. A RAG pipeline consists of three stages: data ingestion, retrieval, generation. Each stage of the RAG pipeline has different components, such as a vector database, an embedding model, an LLM, a prompt template, etc. Let's explore the different components in the various stages of a RAG pipeline. Data ingestion stage. In the data ingestion stage, we have a proprietary dataset, an embedding model, and a vector database. Dataset. The dataset is the task-specific or domain-specific proprietary dataset that contains information to be used by the RAG pipeline while generating query responses. The documents in the dataset are split into small chunks, like paragraphs or sentences, and sent to the embedding model. Embedding model. The embedding model generates vector embeddings for the text chunks in the dataset. Some popular embedding models include Google's Gemini embedding 001 and OpenAI's text embedding 3 small. Vector embeddings. Vector embeddings generated by the embedding model are a numerical representation of text chunks. Each vector embedding represents the semantic meaning of the text from which it was generated. Vector database. The vector database stores and queries data using vector embeddings. We store the input data with vector embeddings and other metadata in the vector database. The vector embeddings stored in the vector database are fetched by a retriever using the vector embedding of the user query. Retrieval stage. When a user asks a query, the retrieval stage in the RAG pipeline fetches relevant documents for the query from the vector database. It has the following components. Query. Query is the input the user gives to the RAG pipeline to get an answer. Embedding model. The embedding model used in the retrieval stage is the same as that used in the ingestion stage. It converts the user query into a vector embedding. Document retriever. A document retriever fetches relevant documents for the query from the vector database. Once we have the relevant documents for the query, the generation stage uses the query and the documents to generate output. Generation stage. In the generation stage of the RAG pipeline, the user query and relevant documents are combined using a prompt template. The combined prompt is then passed to the LLM to generate the output. Prompt template. The prompt template combines the user query and the documents fetched by the retriever to create the final prompt for response generation. LLM. The LLM can be self-hosted or API accessible, like Gemini or OpenAI models. In the final stage of the RAG pipeline, the LLM generates output for the user query using the prompt. With this introduction to the different components of an RAG pipeline, let's discuss how it works. How does a RAG pipeline work? A RAG pipeline has several steps, including data ingestion, document retrieval, query, and document augmentation, and response generation. Data ingestion. We first pre-process our dataset and split it into small chunks, such as paragraphs or sentences, based on their size. Then, we generate embeddings for each chunk in the dataset and store them in the vector database. Data ingestion is an offline process, and it's not needed in the real-time execution of the RAG pipeline. We only need it to add or update data in the database. Data retrieval. When a user asks a query, we need to fetch the relevant documents from the database. To do this, the RAG pipeline first generates the vector embedding for the query. Next, it fetches similar documents from the database. Combining user query and documents, after fetching relevant documents, the RAG pipeline combines them with the query to generate an input prompt for the LLM. Output generation. In the final step of the RAG pipeline, the LLM uses the input prompt containing the query and the fetched documents to generate the response to the query. The response is then passed to the user through the user interface. With this understanding of the components and working of a RAG pipeline, let's build one using LangChain, ChromaDB, and Gemini. Build a RAG pipeline using ChromaDB and LangChain in Python. To build the RAG pipeline, we will first install all the necessary Python modules and obtain the API keys required to access LLMs. Next, we will prepare and ingest the data into the ChromaDB vector database. Finally, we will implement the retrieval and generation stages of the RAG pipeline. You can install all the modules required to build the RAG pipeline by executing the following command in the command line terminal. We will be using Gemini or OpenAI models in our RAG pipeline. If you want to use Gemini models, you can create a Gemini API key. You can create an OpenAI API key if you want to use OpenAI models in your RAG pipeline. After getting the API keys, you can set the environment variables in your Python file as follows. If you are using ChatGPT models, you can set the environment variables using OpenAI API keys as follows. After installing the necessary modules and setting up the environment variables, let's pre-process the dataset. Pre-process dataset. We will use the Bug Republic text file to build the RAG pipeline. Bug Republic is a fictional country whose data isn't publicly known. Hence, any LLM won't be able to answer any question related to the country. Using the information in the text file, we will use a RAG pipeline to answer questions related to Bug Republic. In the first step, we will split the text data into small chunks of 500 characters using the following rules. First, we will split the text into paragraphs. If a paragraph has more than 500 characters, we will split it into sentences. If a sentence has more than 500 characters, we will split the sentence into text strings of 500 characters. To maintain the semantic meaning in the incomplete chunks, we will keep 50 overlapping characters between two chunks. To create the text chunks, we will use the recursive character text splitter function defined in the LangChain.TextSplitter module as follows. It is essential to convert the input text into small chunks as each embedding model has a fixed input token capacity. For instance, the Gemini embedding 001 model has a maximum input token length of 2048. Providing a text chunk longer than the maximum token length to the embedding model truncates the input text while generating vector embeddings, and we lose information. After splitting the input text into small chunks, let's create their vector embeddings and ingest them into the ChromaDB vector database. Insert data into a vector database. We will insert the text chunks into the ChromaDB vector database using the following steps. First, we will initialize a persistent Chroma client using the persistent client function from the Chromad module. The persistent client function takes the file path of the vector database as its input and returns a client object. Next, we will initialize an embedding function using the Google Generative AI embedding function from the chromad.utils.embedding functions module. The Google Generative AI embedding function takes the embedding model name we want to use as its input and returns an embedding function. If you want to use OpenAI embedding models, you can use the OpenAI embedding function to initialize the embedding function. After initializing the embedding function, we will create a ChromaDB collection named Bug Republic to store the data. To do this, we will use the createCollection method, which takes the collection name, the embedding function, and a dictionary containing other metadata as its input. Finally, we will create an ID for each text chunk in the input data and insert them into the vector database using the add method. The add method takes a list of IDs for the input text chunks as input to its IDs parameter and the list of text chunks as input to the documents parameter. After executing the add method, the text data is inserted into the bug republic collection in the ChromaDB vector database. After ingesting the data into the ChromaDB vector database, we can use it to implement the retrieval and generation stages for the RAG pipeline. Build a retriever. We will use the bug republic collection in the ChromaDB vector database to build a retriever in the RAG pipeline that fetches documents relevant to a given query. First, we will create a client to the ChromaDB vector database using the persistent client function. Next, we will initialize an embedding function using the Google Generative AI embeddings function from the LangChain Google Gina module. Here, we must use the same embedding model we used while ingesting data into the ChromaDB vector database. Next, we will build a LangChain vector store using the Chroma client and the embedding function by passing the client embedding function and the ChromaDB collection name as input to the Chroma function from the LangChain Chroma module. Finally, we will build the retriever using the asRetriever method of the vector store. The asRetriever method takes a dictionary of input arguments as input to its search quargs parameter. We will set the input parameter k equals 4, which decides how many relevant documents to fetch for a given query. We get a retriever after executing the asRetriever method, as shown in the following code. After getting the retriever, we will create a document combination chain to combine the user query and the retrieved documents. Create a document chain to combine the query and relevant documents. We will use the following steps to combine the user query and the documents fetched from the vector database. First, we will initialize an LLM using the chat Google Generative AI function from the LangChain Google Gina module. You can use the chat OpenAI function from the LangChain OpenAI module if you want to use ChatGPT models. Next, we will define a prompt template with placeholders for the user query and the fetched documents. To do this, we will use the chat prompt template function from the LangChain.prompts module. After creating the prompt template, we will create a document combination chain using the createStuffDocuments chain function. This function takes the prompt template and the LLM object as its input. During the RAG pipeline's execution, the document combination chain combines the fetched documents and the user query into the prompt template and passes it to the LLM. Finally, we will pass the retriever and the document combination chain to the createRetrieval chain function to create the complete retrieval chain. Using these steps, you can create the prompt template, document combination chain, and the retrieval chain as shown in the following code. After creating the RAG chain, we can use it to answer user queries based on the documents in the vector database. D. Generate output using the RAG pipeline. We can use the invoke method of the RAG chain to generate outputs for user queries as follows. As you can see, the RAG pipeline gives the correct output using the information in the text file that we ingested into the ChromaDB vector database. Thus, we have successfully built the RAG pipeline to answer queries using the input text data. Now, let's look at some real-world applications of RAG pipelines. Real-world use in AI applications that need up-to-date information, facts, and proprietary data. The following are some of the use cases where RAG pipelines can be helpful. Customer support. Building a customer support application requires fetching real-time updates for support tickets and orders and answering user queries based on the order or ticket status. Using RAG pipelines, we can create a customer support application that generates accurate and context-aware responses to maximize customer satisfaction. Healthcare. We can build RAG pipelines using LLMs and medical literature to help healthcare professionals get evidence-based recommendations on patient symptoms, drug interactions, and treatment procedures. This can help them make informed decisions without relying on their memory. Legal document analysis. Like healthcare, we can also build RAG pipelines to provide recommendations for legal issues based on past cases and government policies. This will help law professionals save time in legal research and reduce the risk of overlooking critical information. Education, we can use RAG pipelines to build personal tutors who teach and resolve students' queries by considering their performance, learning speed, and textbook information. This can help students learn easily at their own speed. Enterprise knowledge management, we can build RAG pipelines using wikis, company policies, Confluence pages, product specifications, etc., to help employees easily get answers to queries about proprietary products and company policies. This will help improve productivity by making organizational knowledge easily accessible. That's Tay, and thanks for watching.